All right, we're going to begin chapter 3 with kind of a reminder section. So, given, throughout, it's just going to be, K is just going to be a subfield of C throughout the entire chapter. We can consider polynomials. Polynomials, let's say P of T. Actually, I'm going to keep the notation in the book. They use F and G. It's polynomials over K. Then we say that F divides G if there exists some H of T in K adjoint T such that, G is HF. So F divides G if G is HF, or equivalently, we also will say F is a factor of G. It's another way of saying the same thing. And for two polynomials to divide each other, this is kind of a strong condition that one's a factor of the other. In general, if we took two random polynomials, they aren't going to divide each other. That's, again, a strong condition. So what happens when they don't divide each other is the division algorithm, which I'm just going to state and not prove. It's proved in your book. It's also proved in any ring theory book, which is a prerequisite for this course, so I'm not going to do it. But just as a quick reminder, what it says is let F and G be polynomials in a field with F not 0. We're going to divide F into G, and we don't divide 0 into things. So F is non-zero. Then there exists unique polynomials, Q and R in K adjoint T. I'm omitting the of T notation here, such that F is G is FQ plus R rather. And the degree of R is strictly less than the degree of F. And the proof of this, again, we're not going to do, but it's polynomial long division. It's all just polynomial long division. That's all it is. All right. And the R and Q here are referred to as the remainder, and it's a polynomial. Let me just specify it's a polynomial. And Q is the quotient. And it's also, again, a polynomial. Okay, so we have access to the division algorithm in this ring. That's what that is saying. All right, so let's just do a quick example of that, just to remind you how to do polynomial long division. Let's let G be t to the fourth minus 7t cubed plus 5t squared plus 4. This example is just directly from the book. And then F is t squared plus 3. They do, there's a rather roundabout way of doing polynomial long division in this example. I'm just going to do the long division. So we're going to divide F into G. Okay, so t squared plus 3. We're going to divide that into t to the fourth minus 7t cubed plus 5t squared, and then there's no t's plus 4. That's how we do our polynomial long division. T squared goes in t to the fourth t squared times. We multiply the t squared through. We're going to get t to the fourth plus 3t squared, and then we subtract off that quantity. When we subtract it off, we're going to get negative 7t cubed, and then 5 minus 3 is plus 2. And then I'm going to keep the no t's. Well, I won't even write it. And then we divide t squared in the next highest power. That's this guy. So we'll get negative 7t's when we divide t squared into that. And then we multiply that through. So we get negative 7t cubed, and then minus 21t. Let me write that over slightly. And then we subtract it. So negative 7t cubed, that's going to be 0. 2t squared is positive. And then we're getting negative negative. So that's 21t. Divide t squared into 2t squared, we're going to get plus 2. Multiply the 2 through, we get 2t squared plus 6. And then subtract that quantity. And we're going to get 21t. And then 4 minus 6 is minus 2. Now the degree is less than the degree of t squared plus 3, so we're done. So what did we learn here? Our original polynomial, g, was t to the fourth minus 7t cubed plus 5t squared plus 4. And we found that that's f, which is t squared plus 3. Our quotient q is up here. So this is f. This guy is g. This one is q. So that's t squared minus 7t plus 2. And then plus r, this is our remainder. What's left is the remainder. So that's 21t minus 2. And provided I did my arithmetic right, which I think I did because it agrees with the book, this is how you would apply the division algorithm. All right, so we have a way of dividing polynomials, and if it doesn't go in evenly, sometimes we get a remainder. Great. Definition. Given f and g in k adjoint t, the GCD, the greatest common divisor of f and g, which is going to be denoted by at GCD of f and g, which I'm going to call d, is such that, well, what must happen? Well, d should divide f and g. This is the common divisor condition in greatest common divisor. And then we have a roundabout way of saying greatest, which you should remember from ring theory. Namely, if we have any other divisors of f and g, then e goes into d. So this is the greatest condition. And I'm now going to remind you how to compute the greatest common divisor. So the Euclidean algorithm computes, well, a GCD, there's more than one, of f and g. And what is the Euclidean algorithm? So what you do is as follows. You construct a sequence of remainders. So we're going to initialize r negative 1 to be f, actually to be g, just to keep with the notation sequencing from earlier, and r0 to be f. We're going to repeatedly then use the division algorithm. We're going to use it firstly to divide r0 into r negative 1. So when we do that, we have some quotient, which I'm going to call q1, and some remainder that I'm going to call r1. So really here, this is g and this is f. So we do one division. The degree of r1, I'm just going to note, is less than the degree of r0, which is the degree of f. And then we divide again. We're going to divide r1 into r0. So we can write r0 is r1 times some other quotient q2 plus r2, and the degree of r2 is less than the degree of the thing that was the divisor. The degree of the divisor is the degree of r1. And you keep doing this. Keep dividing. Let me make sure my indices are right. You just keep dividing, and each time when you divide, the degree of the remainder goes down, strictly decreases. And eventually what you're going to get is you're going to get that you're going to get to a point where S, where you have RS minus 1 is RS plus 1, Q, or RS rather. RS, yep, QI plus 1 plus RS plus 1, where RS plus 1 is not 0. But when you divide one more time, you get 0. The Euclidean algorithm says then that RS plus 1, the previous remainder, is the GCD of f and g. So the division algorithm is used repeatedly to get a bunch of remainders, and you keep sort of dividing the new remainder into the old one until eventually you get 0. And when you get 0, the GCD is the previous remainder. Okay, and it's a standard proof that the Euclidean algorithm does indeed compute the GCD. That we're not going to do, but it's in any ring theory book. All right.